Thanks for downloading a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online. Now stay tuned for your 3CR podcast.
Hello and welcome to another episode of Lost in Science. This is 30 minutes of some of the best, some of the greatest science that you're going to hear all week, I reckon. My name is Claire, and on the show this week, of course, we have Stu and Chris with us. Hello.
Hello.
Hi.
Now, Stu, I know you always bring the things that interest you most to us on a weekly basis. So what do you have for us this week?
Well, actually, Chris inspired me. Chris is the wind beneath my wings this week. He was talking about sleep last week, and it got into my head, you know, we apparently don't know much about sleep, but surely the medical guys have gotten in there and they're fully working on it and they can solve the problem of sleep. You know, we've got sleeping pills, we've got anesthetic, we've got painkillers. Surely we understand how all these things work. Turns out, not so much. So I'm going to look a little bit about how the extent of how little we understand sleep extends to other workings of our brain, and some of the common things which doctors will treat us with are not really all that well understood.
Right, fascinating. More deep diving into deep sleep. I love it. And Chris, what do you have for us this week? Some fascinating science, no doubt.
Well, I have another common thing that's not well understood. It's a chemical you may be very familiar with.
Okay. A chemical I'm familiar with.
Yeah.
What could that be?
Is it dihydrogen monoxide?
It could be. It's actually oxidane.
Oxidane?
Which is another name for
oxidane?
dihydrogen monoxide, to be honest.
Which is another name for?
Oh, yes, H2O, good old water. Yes, according to the
Good old
international...
water. I mean, we're trying to take the science to the masses here, so we can use its common name.
Yeah, okay, true. But according to the International Union of Pure and Applied Chemistry, the IUPAC, which is runs, they're the big cartel that runs chemistry, I guess. Big chem. Big chem. They say that oxidane is one of the official names of H2O along with water, whereas dihydrogen monoxide is like a joke name.
Sure.
To people.
Yeah. But, I mean, just because Big Chem say it is doesn't mean it is, though. That's all I'm
just
saying.
maintain, if you want to look smart, start talking about oxidane. It's, the oxidane tap is leaking, or,
dear.
Some oxidane falling from the sky today.
And other terrible jokes that you won't get away with.
Anyway, look, whether you call it oxidane or water or dihydrogen monoxide, it is a very unusual substance, good old water. So I'm going to look at some of the weird things about it, some of the things you may not know about it, some of the things in its liquid and solid forms, things that we are still discovering, and also ask a question, where does it even come from?
Well, I'm looking forward to hearing where it does come from, because I thought it just came from the sky.
Or from the tap, yeah.
Or from the tap. Either one is normally pretty reliable depending on where you are. I am, getting thirsty just thinking about that story, so on with the show.
Chris, you were talking last week about sleep and how, in a lot of ways, it remains a mystery to science why we actually sleep at all, and even why we need to spend so much of our time doing it.
Yeah, we just lie down in a dark room with our eyes shut and just think that's completely normal.
Yeah, and about a third of our time,
yeah,
more or less, is spent doing this activity that we don't understand. But it got me thinking about all the ways that science has come up with to induce sleep in people, including what we would commonly call sleeping pills, which led me to find out there are a lot of things called sleeping pills, in fact. First of all, prescription medication is not recommended for the long-term treatment of sleeplessness. They would rather, use various other therapies and behavioural changes. That's typically what the doctor orders in those cases of long-term sleeplessness. But in other situations where sleep disruption is temporary, and look, I'm not sure if growing babies comes into the temporary category, but there are a range of pharmaceuticals that might be used, and some of them help people fall asleep, some of them help people stay asleep, but they're all quite different chemicals, apparently, with different modes of action. The main thing they have in common, with only a couple of exceptions, and is one thing why doctors don't like to prescribe them, is they all seem to lead to dependence on the sleeping pills, and obviously doctors want to avoid medications that lead to dependence, especially for something which is such a basic requirement as getting enough sleep. So sleeping pills are kind of the last resort, but we do have things that can make you fall asleep and help keep you asleep, and various different substances will do one or the other or both, which is also quite a tricky thing. Some things help you fall asleep, which is a good thing, but if you wake up easily and that's why you're not getting any sleep, that's not going to help you much. And other ones keep you asleep once you've fallen asleep, but they don't actually necessarily help you fall asleep in the first place, which is also not such a great option either.
So these different sleeping pills, do they act on the same parts of the brain, or do we even know what they do in the brain?
Look, they do. They act on various different functions of the brain. They do all have relatively similar actions, but they do also act in slightly different ways. So the chemical reactions they cause are all slightly different, even though they're causing the same end point. They're actually from different chemicals. There's a whole lot of stuff. I could do a whole story on that. But what I also sort of stumbled across while I was looking into medical approaches to sleep was that there are times when doctors need to put people to sleep to fix other problems. So talking about things where sleeplessness is not the problem, talking about things like surgical procedures where they need to do things which are not all that pleasant, and it's better if people are not aware of what's happening to them as it's happening, so to speak. So when people do need surgery that would cause them distress, a special crew is called in to administer an anaesthetic, which is something which, they give you an anaesthetic which basically shuts down your senses. That's what the word anaesthetic means. And the lack of consciousness, particularly the lack of pain, allows surgeons to perform procedures which would otherwise be distressing and uncomfortable or very painful if you were fully conscious of what was going on. But even the name, as I said, the name anaesthetic means something else, because when we're asleep we can be woken up by loud noises or bright lights, or if someone sort of jumps on you or punches you in the arm or something, you'll wake up because your senses are still active.
Or they're just they cut open your belly or something like that.
Yeah, quite a different sort of sleep, I guess, if you even can call it sleep. It's much more of a lack of consciousness than just being asleep. But anaesthetics stop all of those sensory inputs almost completely. And again, there are a range of them. So there was first demonstrations of things like ether and chloroform in the 19th century. There's much more modern drugs which have the effect of a general anaesthetic, which is what we're referring to here. And also there were various substances much earlier than this, than the Western medicine in Japan, which were apparently based on a range of psychoactive plants combined in a certain way. This exact recipe seems to have been a bit lost, so it's kind of a bit hard to compare with current medical practices. This was developed by people whose names are available if you want to go and look it up, but they're not really used in what we'd call modern medicine, I suppose. But the compounds used to induce general anaesthesia themselves are actually not very well understood. At least the way they function in the brain to bring about this state of unconsciousness is something of a mystery. And that in itself is a bit of a scientific problem, especially in medical research. If you're trying to get better treatment for something, you want to know how it works so you can find other substances that will do the same thing, only better or safer or whatever it might be that you're trying to improve on. And if you don't understand how it works, that makes that task very difficult. You don't even know what specifically you're looking for because you don't know what it's doing to the patient in the first place. But there was a paper published in the Annual Review of Neuroscience back in 2011, so it's quite some time ago, that looked at multiple anesthetics used in surgery in modern medicine around the world, and they found they all seemed to act on multiple targets in the brain simultaneously. So they're not just doing one thing that is the effective action of the medicine. They're doing multiple things all at once. And what they focused on was how each individual action worked in the patients. So because there is no single effect, that's part of the reason we don't understand what they do. What they did do, these authors identified multiple states of anaesthetized patients under the effect of these various anesthetics. So they gave them all names: sedation, unconsciousness, pharmacologic non-REM sleep was another state that they identified. And they had all these different names for slightly different actions on the brain and how the body responded to them. But what they suggested in their paper was that each category of anaesthesis could be identified separately, and then you could tease out the different modes of action and figure out how to maybe improve those as individual things. But it's still quite a hard thing to do when you've got multiple chemicals, and we kind of just stumbled across them because we didn't really know what we were looking for when we found them.
It's also the kind of thing that anesthesia it's a pretty delicate process as well, because it is that balance of getting people to the right state of unconsciousness but not too far in, or you don't want them to die as a result of the anesthetic either.
Yeah, you want those higher brain functions to shut down and the more animal brain functions to keep pumping your blood and inflating your lungs and all of those things. But it's obvious that general anaesthetic has revolutionised surgical practice, allowing for operations that would have been impossible without the ability to anaesthetise people. And it's obviously extended and improved the lives of millions of people since the middle of the 19th century. And that's even without understanding how they worked. So the benefits have been pretty obvious. Even if the processes are not well understood, the benefits of the anaesthetic outweighs the risks, which have also been, studied and analysed in medical research over the years. But obviously general anaesthetic is not something you would take yourself for pain relief. It's a very difficult and, as you say, complex balancing act. It's an important job to be an anaesthetist, and not everyone is cut out for that task, obviously. So if we just wanted some pain relief, we'd grab something simple, something you could just pick up off a supermarket shelf, like, I don't know,
like paracetamol
or something.
Yeah.
Panadol, some similar brand, which is a drug called acetaminophen. And we obviously know how that works exactly because it's such a commonly and readily available drug, except that we actually don't really know how acetaminophen works at all. So unlike aspirin or ibuprofen, which block pain-causing enzymes and prevent inflammation directly, the effect of acetaminophen is still something of an unknown. It's not. There are a number of theories on how it works, but nobody's quite nailed down the exact mode that it acts.
So acetaminophen, is that the same as paracetamol? Is that another name, or...?
They're basically interchangeable names in the drug classification system.
We should talk to the International Union of Pure and Applied Chemistry and see what they say.
I think it was interesting, and this is why it sort of caught my interest, that in medical science, showing that something works and showing that its side effects are not as bad as the illness that it's helping treat or prevent has often led to widespread adoption in the practice of medicine, even if not everybody, including the doctors, know how they actually work.
Yes, you're listening to Lost in Science, and I am talking about water, aka oxidane, aka dihydrogen monoxide. And water is, obviously, it's a very important chemical in our lives, in the world. It covers approximately 70.9% of the Earth's surface. And our bodies contain, well, somewhere between 55 to 78% of water, depending on your individual composition and body size and that kind of stuff.
That's a lot of water.
It's a lot of water. There's a lot of water in our lives and in our world. And it has a lot of unusual properties. Like, it's often called a universal solvent because it dissolves so many things, including itself. Bit of a shout out there, Stu, to your story from a couple of weeks ago. You talked about alkaline water, and you talked about how water has ions of hydrogen and hydroxide in it. So basically, it has dissolved itself or self-ionized within itself, which is kind of a weird thing. It has an unusually high boiling point for its molecular size, perhaps due to the bonds that form between the hydrogen atoms within the water molecules. And that also leads to it having a high surface tension, which allows it to do things like capillary action, which, you know, can climb up trees and that kind of stuff.
One of the ways I describe that when I'm teaching about water and capillary action, which is very important for plant growth and stuff like that, is that water sticks to itself really well, and it sticks to other things really well. Yeah.
Well, the sticking to other things really well is what we call getting wet. Yeah, so it's a really obvious thing, but it's actually quite an unusual property. What else? It's incompressible, pretty much, in its liquid form, but it gets less dense when it freezes to ice, so it expands, whereas most substances, when they go from liquid to solid, they get more dense because they're, you know, concentrating or they're condensing. So look, there is a lot more going on with water than even that. So look, let's look at ice. Guy mentioned ice there, and as I said, it gets less dense when it freezes, and that seems to be due to the nature of the hexagonal crystal structure that ice is made out of, which itself is due to the angles of the hydrogen molecule. So you might have seen like pictures of the hydrogen molecule, the water molecule. They have like the two hydrogen atoms and oxygen. They kind of look like a Mickey Mouse thing. Yeah. So to arrange that in kind of a crystalline structure, you kind of get this weird sort of these hexagonal rings, but then they join up in a kind of almost tetrahedral shape to other kind of hexagonal rings. And so that's as a result, it kind of gets this larger crystal structure, which makes it less dense than the liquid form. But that is merely one kind of ice. That is just merely the most common form of ice, which is known as ice 1H.
What happened to ice 1A, B, C, D?
Well, the H stands for hexagonal, Stu.
Okay. All right. That's all right then. That makes a lot more sense.
So, for instance, there is a cubic form, ice 1C, which is believed to exist in the upper atmosphere. I think it's more kind of theorized in that sense. The verified samples of it were only first obtained in 2020. So it's only recently been actually verified as being existing as a real thing.
Has anyone tried to artificially make that?
Well, that is the artificially making it. I think they've
okay, right.
But yeah, the fact that it's called ice 1H and ice 1C does suggest there may be more numbers involved. These are Roman numerals, I should say. So how many there are, it seems to go either to XIX 19 or XX 20, depending on who you listen to. I'm not going to go through all 19 or 20 of these ices, but I'll give you a couple of highlights. There is ice 7, sometimes known as hot ice. It's also a cubic crystal, but it is formed from liquid water at high pressure, so above 3 gigapascals, which is about 30,000 atmospheres. So you have liquid water at that high pressures and your lowest temperature to room temperature.
Is this the one that they've they've theorized is in space, in various places in space. Is that what?
It is one of the ones to be theorized in various places in space. It is thought to maybe comprise the ocean floor of Europa, but it has been found on Earth. So in 2018, they found it inside diamonds. So the idea is that water was trapped inside the diamonds inside the Earth, in the deep mantle. And so the high pressure of the mantle trapped the ice, and it was kept there inside the rigid diamond lattice. And then when the diamonds come to the surface and cool down to surface temperatures, you get that high pressure environment still stored within the diamond, but without the high temperature. And so you get this, what they call hot ice, but it's not that hot, it's room temperature, which is hot for ice.
That's pretty warm for ice, yeah. Try leaving an ice cube on the table.
But it does get hotter than that. And then there is another interesting one, is superionic ice, or ice 18. Now, this is predicted to exist at higher temperatures and pressures, so around about 1,000 Kelvin and 40 gigapascals. So I said 3 gigapascals at 30,000 atmospheres. This is 40 gigapascals. That is, 400,000 atmospheres of Earth. So this one, basically, it kind of has a solid lattice of oxygen atoms, and the hydrogen ions, which are basically just protons, can move freely throughout this lattice of oxygen atoms.
And I think I touched on this in a story maybe last year, and they think they may be able to use that to make proton beams, or it would be theoretically possible to make proton beams out of using this substance, and you could use it as a kind of alternate electrical circuitry with protons rather than electrons being the moving particles in the system.
Well, I mean, obviously you'd have to keep it at those high temperatures and pressures. I mean, this is another one that's believed to be found in space. It could be inside the interiors of Uranus and Neptune. And the fact that you have these fast moving protons could help generate these strong magnetic fields that these giant planets have. So yeah, that's the numbering of ice. Like I said, there are a few that fall outside the numbering system. An interesting one is amorphous ice, which is ice that actually lacks a crystal structure. May, in fact, though, be the most common form of ice in the universe. But
where is it then?
Oh, basically, okay, there's a couple of different kinds of amorphous ice. There's not just one kind. This is where it gets interesting. So there's 3 kinds, in fact. There is low density amorphous ice, which forms at atmospheric pressure or below. And then there is high density amorphous ice and very high density amorphous ice, which forms at higher pressures. The low density amorphous ice forms by extremely quick cooling of liquid water, or by depositing water vapor on very cold substrates. Or you can do it also by heating higher density forms of ice, and you can get this kind of amorphous structure. It's a bit of a weird one in that sense, but it has these different kind of density forms. So the main ones are the low density and the high density, and it can switch between these different forms under different circumstances. And the fact that it has these 2 different density forms of amorphous ice led some researchers from Stockholm University in 2017 to look at the way it transitions, and they basically found evidence that it kind of, in the way that it transitions, that there is kind of a liquid equivalent of this ice, amorphous ice, and suggests that liquid water itself has both these high and low density forms, which may exist together at the same time and may account for some of its unusual properties, because it's not just one liquid then, it's kind of 2 liquids that interact together.
That have kind of dissolved into each other, or they're just filling in the gaps.
Yeah, that's right.
Between one and the other. Wow.
I can't find that this is a consensus in the community that this is how water works. But it gives you an idea of how complicated this very common, simple substance is. I also haven't been able to figure out whether it is, these unusual properties is what makes it so important for life, and why, we exist on a planet where there is so much water, or if it just seems so unusual because there is so much water and we have studied it a lot. So I don't know, maybe if we studied other substances in the depth we've studied water depth, then we'd find some interesting things as well. But yeah, it is all around us, and where it actually comes from is still another kind of mystery that we're trying to solve. Because, we know that the Earth formed in the early days of the solar system from bits of rock and dust that was floating around. But the Earth was also very hot, and, water would have evaporated from the surface, and so it needs to have been deposited somehow on the surface as the Earth cooled. And we've looked at things like comets and asteroids, which all contain water in various quantities. But getting the right kind of isotope makeup of the water that matches what we see on Earth is tricky. There aren't many asteroids that have kind of a composition that's similar to what we see on Earth. And they're quite rare. So it seems a lot of people suggest that it seems unlikely that it's come from that form. But there was a new study that was just recently published from researchers from Curtin University. He looked at samples that were brought back from an asteroid, and they found that water can actually form on the surface of some of these space rocks due to the action of the solar wind, essentially. That you have essentially hydrogen given out by the sun, that bombards these rocks. A very common mineral called olivine, which is found all throughout the Earth as well. And so the hydrogen bombards it, and it breaks down the molecules of olivine or olivine on the surface, and to create water, essentially. You get the thin layer of water over the surface of these asteroids. And so they're suggesting that perhaps this could be a mechanism that water has been created on these rocks, and then they have come to Earth. Again, it seems unlikely you might get enough water that way, so this is not a consensus view. This is just a recent kind of hypothesis being put out there. But it's interesting in that there does seem to be ways to create water, essentially, out in space that may have led to it being kind of brought to Earth. Yeah, so look, it is a mysterious substance, water. It's something that, as I said, life depends on it. We look for it around the universe, and we're trying to find where life could exist. But just like our acetaminophen and paracetamol and our anesthetics, we don't really understand how it works, and there are many, many other kinds out there that I'm sure there are still to discover.
And that's all we have time for on another episode of Lost in Science. Lost in Science is recorded on the lands of the Kulin Nation in the studios of 3CR Melbourne and broadcast across Australia on the Community Radio Network with the kind support of the Community Broadcasting Foundation. If you would like to get in touch with us, we would love to hear from you. You can email us at lostinsci@gmail.com. You can find us on Twitter, where we are Lost in Science 1, or on Facebook, where we are Lost in Science on 3CR. Or you can find us wherever you found us today, again next week, when Claire, Stu and Chris get lost in science.
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.